Yeah, so what we do is we are pretty much in the same space, the SIP, voice over IP, machine learning space, and a lot of what I'm doing is building all kinds of interesting model on the data that we have. So this talk, in a sense, segues very nicely into Scott's talk. Scott kind of scared you all with IoT devices and how insecure they are. So while we don't talk about security per se in this work, I will mention that a lot of this work, because it's based on predictive modeling of when the IoT device would contact the network, we can actually build a security infrastructure out of this, because if the IoT devices are contacting the network more than the frequency that they used to contact with, you know something is going wrong. So the Mirai botnet attack, for instance, could have been at least we would have had an advanced warning if we had some sort of models built based on access patterns. So this is what I'll be talking about today. And my student actually went crazy and built all kinds of builds on this, so I do apologize. I'll probably go through many of these builds. But the basic idea here today is that if you take a look at IoT, depending on if you're an optimistic or pessimistic, anywhere from 32 billion to 99 billion devices, right? I don't know how good that number is, but everybody throws around these numbers. Now, optimistically speaking, you might have about 4 billion devices that use cellular IoT as their main access mechanism, anywhere from 4 to 26 billion cellular IoT devices. And my interest is in the cellular space, or IoT devices that are going to use cellular network, cellular internet as their access to the network. I'm not going to bore you with all what IoT does, indoor, outdoor, blah, 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 so I'll skip that. But basically, if you take a look at cellular networks, you have something along what you see here. You have access network. You have these UEs coming in through the access network. Then you have the core network, and you have the internet. Now, as the UEs come in through the core network, one of the entities that they talk to is this thing called the MME, or mobility multimedia entity, right? So what the MME does is it serves as the brain of the core network that the cellular network operator provides. So the MME is the one that decides what type of bearer traffic to assign to UEs. The MME is the one that sends out messages to HSS, the home subscriber system, to authenticate the UE. The MME that is the one that sets up the channels with the signaling gateway and the packet gateway, so the packets can go back and forth from the UE across the air interface to the internet and back. So the MME is fairly involved in setting up these sessions, and any type of UE, be it a mobile phone or a cellular IoT device, or that little USB dongle that you put on your PC to get on the cellular internet, any of those devices necessarily hits the MME. So we focus on the MME and we try to see what is going on there that we can leverage to do a modeling of cellular IoT. Now, what the MME does is it keeps session state. So for each mobile device that is active on the network, MME maintains the session state. And by session state, we mean when the mobile device registers with the network, what type of bearer channels it has established, what type of policing to do on it. So there's a bunch of information that the MME maintains from the session state point of view. Now, clearly, the session state takes space. It's not free. And an operator would like to dedicate most of their resources at the MME on phones, right? Anything that the phone does when it goes on the internet, when you move, when you make a call, the MME is involved. So the operator would like to dedicate most of their resources, if not all of their resources, to actual phones instead of these cellular IoT devices who contact the network on a temporary basis and are not there all the time. So what we wanted to do was to see that if we are going to have these billions of IoT devices come online, we do not want to use the scarce resources in an MME to handle those devices. Instead, we want to offload those devices' session state to a data lake and optimistically prefetch that session state before the device contacts the network. And the device is going to contact the network essentially any time that the device is going to send some data to the network. So that was our problem. How to dedicate most of the MME resources to UEs that are non-cIoT, but still support cIoT or cellular IoT devices without sacrificing the quality of experience we give to non-cIoT devices. And if you take a look at MME, MME is not necessarily a CPU-bound entity. It's more a memory-bound entity because we have to keep the sessions of all these UEs alive quite a bit. So given that background, one way to deal with it is to just linearly increase the MME depending on how many cellular IoT devices it wants to handle. Now, clearly, that's not efficient use of computing resources because some IoT devices are going to be bursty, some are going to be regular, some are going to be semi-regular. So there's no need to linearly scale it because that's a cost that the operator has to bear. Instead, what we show is that we can use logarithmic or sublinear increase in MME resources to handle cellular IoT devices. So a lot of what I'm talking here is actually described. Carol knows me and Scott knows me. Anything I do, I end up publishing some sort of an academic paper on it. So a lot of what I'm describing here is described in this paper that was published earlier this year and presented at the ICCCN conference. If you're interested, by all means, send me email and I'll be happy to send you that paper. So this work was done, obviously, when I was at Bell Labs, along with my colleague Yu and Samir. But I also had a summer intern working with me last summer from the University of Massachusetts at Amherst. He graduated with a PhD, but he was working with me at that time. And a lot of this work was done by him. So, all right, so here we are. So now, in order to implement this prefetching scheme, essentially, we need two things. One thing we need is, when do we prefetch? So in this example, if you see, we are not prefetching right now. We have our memory pool in the MME, which is full. All the slots are occupied by session state corresponding to something. That something could be a cellular IoT device, or that something could be a UE. At a certain time, a request comes in, and we have two requests here coming in. So clearly, everything is full. So we have to eject one of the session states. So we see that there's an orange request coming in. We fetch the context of the orange request. We notice that we don't have any space in our buffers. So we eject the green request and service the orange request. So under this type of regime, we already had the red request in memory, so we didn't have to eject anything. So our hits were 1 and our misses were 1. Now, assuming that we had prefetching, then with prefetching, what would typically happen is we would know that an orange request was going to come. So we would prefetch that request. We would eject the green request before the actual request from the orange device came in. Under such a regime, you essentially have 2 hits and no misses. Because by the time the orange request came in, we already optimistically prefetched the session state from the data lake, and the red request was already in memory. So we know that prefetching can help, but the question is to what extent can it help? So where do we look for inspiration? Well, prefetching is not new, neither is replacement new. So notice there's 2 things going on here. First, we are prefetching from the data store. And secondly, we are ejecting somebody to make space for the newly prefetched session state. So there's prefetching and there's replacement. These 2 things are what we need to figure out what other people have done in the past. So if you take a look at prefetching, clearly operating systems do it all the time. They have various prefetching strategies. They have locality of reference. If you take a look at an operating system and see how it ejects its pages from memory to make space for other pages belonging to a process, it's a solved deal there. If you take a look at replacement policies, there's various replacement policies. There's least recently used, most recently used, first in, first out, random, etc. So when an operating system is deciding which page to eject, it'll use one of these replacement policies. And I suspect you can figure out what least recently used, most recently used, first in, first out, etc. are. Now tied to this is an algorithm called Beladi's algorithm. Beladi's algorithm is essentially a perfect replacement policy. So what these replacement policies do, all of them, is they replace the session state or the page that hasn't been accessed the longest. Right? Least recently used takes a look at the pages that were accessed many, many cycles ago and ejects those. Most recently used ejects the recently used ones. So what Beladi's algorithm does is it switches this thing and say instead of ejecting the pages that were used in the past, what if I eject a page that is not going to be used much in the future? Right? So do you see that distinction? So instead of looking at the past, I'll see in the future which page is going to be used far in the future, and I'll eject that. Well, the problem with Beladi's algorithm and it's essentially is that you don't know how far in the future to go. Is it 2 seconds? Is it 10 seconds? Is it 20 seconds? Right? So in a sense, what we are trying to do is to approximate Beladi's algorithm with our approach here, with our learning approach. All right, so what do we do? So we model each IoT device separately, and I'll talk about a class of IoT devices that we modeled. But essentially, in the first step, for each IoT device, we use a neural network to learn when it's going to make a prediction. And the way we learn when it's going to make a prediction is to take a look at its last n predictions. And we set n is to 3. So we take a look at the last 3 or 4 times that it accessed the network, figure out the difference between those access patterns, and train a neural network model based on that. So once we have trained a model, then we evaluate the memory performance of the model under various regimes of replacement, LRU, MRU, random, and so on, and see which one works the best. So by now, I guess many people have talked about neural networks at this conference. You guys know what a neural network is. So I'm not going to spend too much time on it, but MLP, or Multilayer Perceptron, is the simplest of a neural network that you could imagine. It has, obviously, your input layer and 1 or 2 hidden layers. It's not a deep neural network, so it's not a convolutional neural network or a recurrent neural network or all these deep neural networks which have a bunch of hidden layers. It's very simple. And then it has what I typically call a squashing function, either sigmoid or a tan, that essentially takes the input and maps it to a range of either 0 to 1 or -1 to 1. And then it figures out how close I am by running a function to see how far it did from the actual value, the loss function, and then it adjusts the weights in a normal backward propagation approach. So nothing new here. It's a very, very simple neural network. So what we did is we took our training data, and I'll talk more about that in a bit, trained the model, took our testing data, applied it to the model, and figured out the time of the next request. And before that time arrives, we would fetch the request from memory. So then we would simulate these device models, these IoT devices, sending us a list of prefetch requests. And if the list of prefetch requests in a certain time window is greater than the memory slots available, we would eject one of the memory slots and preemptively put the request in that is going to probabilistically happen, that's going to happen next with the highest probability. All right, so that's the idea, basically. For the data sets, the interesting thing is that there are no public IoT data sets, cellular IoT data sets. GSM, which is the telephone system commonly used in Europe, has some data sets, but they were not publicly available. CDMA, at this time when I was doing this work, I was still at Bell Labs, so we had some internal data sets, but again, they were not public, and they were mostly generated in our laboratory. So there isn't any widely deployed cellular IoT infrastructure today where we can get a data set from. So what we did is we took a look at publicly available data sets, and these are not cellular IoT data sets, but we can simulate these to be cellular IoT data sets. So we took 5 data sets. The first is a Pecan Street data set, and this is a smart meter. So its frequency is very regular. Every minute in an area, I believe this was done in Boston on Pecan Street, every IoT device in that area, every minute sends a request to the network. So we simulated that request as an IoT device request arriving at the network. So Pecan Street gave us a very regular heartbeat type of mechanism. IoT devices contact the network every minute. Weather underground was semi-regular in the sense that every 5 minutes to an hour, a bunch of weather stations would upload their data to Weather Underground, and from there it will send it to all the other computers that are displaying weather on your phones or on your PCs. So every time an upload happened, we would consider that to be an IoT request, and imagine that a Weather Underground station was making a request of the cellular network. So whereas this was very regular, this was semi-regular. GeoLife is another data set that has GPS mounted on cabs in New York City, and every time the GPS changes, we simulate that as an IoT request. Because this is GPS, and because it's in the city, and because it's mounted on cars, it's bursty, because the same car would be traveling at high speed, generating a lot of these events. Then we had an Austin traffic data set. This was a data set that was collected from RFID transmitters in cars, and RFID receiver mounted at a signal post or a signaling post in a street in Austin, and every time the car would go there, underneath that signal mechanism, it would essentially simulate an IoT access. And this was cyclical. The difference, the inter-arrival time, was sometimes between 2 seconds or 2 hours. At night, there would not be many cars going through, so it would be a fairly cyclical pattern at night, and cyclical pattern in the day with inter-arrival request of 2 seconds. And then we had the Divvy Bikes data set collected from the city of Chicago. And here, every time a Divvy bike is either put into the bike holder or taken out, we would count that as a cellular IoT request. For some stations in Chicago, you typically saw many of these events happening. For other stations where there was not too much traffic, you would see very less number of requests happening per unit time. So we would consider this Divvy bikes as a random trigger. So these 5 data sets essentially encompassed every type of cellular IoT device that you're going to find. Some devices are going to be cyclical, some are going to be very regular, some are going to be random, some are going to be bursty. So we believe we captured all the variations that these IoT devices can look at. All in all, we analyzed about 15 million IoT requests. The data set was collected for 120 days. So we used 80 days for testing and 40 days for training. 80 days for training and 40 days for testing. Because the number of devices within each data set varied, we basically sampled 65 devices from each data set to have a total of 325 devices. So 65 times 5 is 325. The reason we stuck with 65 devices is because we did not want to bias the training set, because some devices, some data sets had lots of devices, others didn't have as many devices. So this is the data set description. And then the question is, how do we measure performance? So we can measure performance various ways. The canonical ways to measure performance is the hit rate, which is the fraction of requests found in memory. Consequently, the miss rate is 1 minus the hit rate. 5 minutes, 10 minutes? So besides these canonical metrics, we came out with a new metric we called the value of perfect information. This is essentially the percentage reduction in hits with the proposed algorithm over optimal prefetching. So in a sense, if you take a look at the denominator, let's assume that you have an oracle sitting there that's telling you when each IoT device is going to come and contact the network. That would be optimal prefetching. We know for sure when the device is coming. So if we subject our algorithm and see how close it comes to the optimal algorithm, and we take the ratio of those and turn that into a percent, you essentially have the value of perfect information. So notice the denominator is going to be, you're never going to do more than the denominator. So in the best case, your value of perfect information will be 0 because your algorithm will be equal to the optimal algorithm, giving you VPI of 0. In the worst case, it'll be obviously a little bit bigger than 0. But what we want to do is to keep our metric value closer to 0 as possible. All right, so once we had all this defined, then we started to evaluate it, and we asked a bunch of questions. Does prefetching help? If so, by how much? Which of the 3 or 4 context replacement algorithms are best suited for this class of traffic? And how does the performance improve as we increase the memory slots? Now remember, we cannot continue to increase the memory slot. If you have 325 devices and we have 325 memory slots, then you don't need to eject anything because you have as many memory slots as there are devices. But memory slots are expensive, and we do not want to scale linearly. So we would like to have less number of memory slots compared to the number of devices we have, right? So we are interested to see for 325 devices, is 20 memory slots okay? Is 40 okay? Or is 60 better? You know, obviously the higher we go, the less hits or the more hits and the less ejections will happen, but we do not want to go too high for the reason that it's not optimal to do so. So overall, we did 60 evaluations. 60 comes from 3 device models multiplied by 4 context replacement policies multiplied by 5 memory sizes. So we did a fairly exhaustive search across our space to see which evaluation performed better. So this is the value of perfect information of no prefetching. So now let me explain this a bit to you. So remember that VPI is a percentage reduction in hits with the proposed algorithm or optimal prefetching. So if we implement our algorithm, how many less hits do we have to do? Recall also that the VPI of optimal prefetching is 0, as I said. So clearly, the closer the value is to 0, the better it is, right? So if we didn't have prefetching at all, there was no prefetching, what would our VPI be? Our VPI would be right here. LRU gives us the best VPI, and I'll explain why LRU. And as you can see, first, as we have more memory slots, your VPI goes closer and closer to 0 as expected. But in this particular case, we use the LRU, and I'll explain why in a second. So the takeaway is that hits reduced by 40% with no prefetching. If I didn't have prefetching, my VPI is 40. If I had prefetching, I would like my VPI to be less than 40. I'll come back to this slide in a second because I want to present what our results were. So these are our results. These are our results. Essentially, the orange here is no prefetching, and the blue here is our multilayer perceptron, our neural network. And as you can see, a couple things. As memory size increases, we do better because the VPI keeps on falling as the memory size increases. Furthermore, the decrease in VPI from memory size of 60 to 80 to 100 remains about constant, which seems to suggest that for 325 devices, if I had 60 memory slots, I'm doing reasonably good. My system is pretty stable, right? If I get 80 memory slot, I don't see too much of a decrease. If I get 100 memory slot, again, I don't see too much of a decrease. So 60 seems to be a reasonable number of memory slots to have for 325 devices. Now, can you linearly scale that up? So for 1 billion devices, you will need, X. I don't know. We have to run those simulations. And that's the continuing work that we are doing. Well, the takeaway here is that look at the value at 60. It's below 20. If we didn't have prefetching, our VPI was 40. With prefetching under a neural network, our VPI is 20. So clearly, we are heading in the right direction. Now, why did we pick LRU as our replacement policy? That is driven by this slide right here. If you take a look at this slide, what it does is it takes all of the replacement policies and tries to see which one is best. So if your replacement policy is close to 0, it's best because the miss ratio is close to 0. So here, as you can see, the green one, hopefully you can see the green is usually the replacement policy that turns out to be the best, and that belongs to the LRU. So, so this is the beginning of the work. We have presented the results at the conference I told you about, and we are actually working on putting recurrent neural networks and long short-term memory models in deep learning to see if we can even reduce the VPI to be close to 0 as possible. I think that is it.
Inspirational, actually. I think
a lot of perspiration.
Yeah, plenty of perspiration. Quite interesting, and shows what we can do as I would call us the engine for innovation, because without this kind of studies, which we're trying to also do for our indoor location, then you're still on the drawing board. Right. So this is really, really exciting work. Thanks a lot. I'm afraid we don't have time right now for questions. But you can. He's going to be here. We're going to take a break after we hear from Lawrence Cast from Verizon. And he's a manager and a solutions architect. Lawrence and I are just meeting, actually. And we're delighted to have him here. And